Okay, cool. Thanks. Yeah, thanks, Job, for inviting me. And so many people here. This is so nice. I had a dream this morning that only 4 people came to the talk. It was me, Job, Ronald, Dion, you were there, and Caroline, right? So, and then because there was so little of us, Job was like, "Oh, let's go do it in his living room at home." So we went and we had tea, which, like, as I'm describing, it sounds really nice. It was actually a nightmare, right? Because I was like, "Why didn't anyone come to the talk? Oh my god!" And then I woke up and I realized, okay, good, I still have to give the talk. So it's very nice to see like more than 4 people. And yeah, there's a couple of things I want to say before I actually go into the talk. So the first one is I've been here now for 6 months. So I'm not new in QuSoft. I don't think I can say this. And I would really like to collaborate with people in the group. So if anything I say, like, you know, is of interest to you, or you have a research question in mind that's sort of related, and you need a lonely postdoc to do the legwork, then like just let me know. I'd love to start a collaboration. And the second thing is I've asked Ronald for some feedback because I will give this talk again next week. So if there's anything that I say that sounds a little bit weird or confusing or is incorrect, like please ask about it and correct me, because yeah, this would be super helpful. And now that I'm part of QSoft, don't let me embarrass us, right? So in a public forum. Okay, good. So that's all I wanted to say. And now I'll tell you a little bit about what I mean when I say quantum backpropagation. This is probably not even the correct way to use this word, backpropagation, and a little bit about this idea of using information in a parameterized quantum circuit, which I tried to draw very badly over there. So this work mostly came out of an internship that I did towards the end of my PhD with the Google team. And then Robert and Robbie from Caltech joined the project as well. So we submitted to NeurIPS and they accepted us, which is great. So NeurIPS is a machine learning conference that classical people care a lot about. So it's nice that something quantum got in there. And I think it mostly got in because classical people are so sick of the hype around quantum machine learning results. And what we say is something a little bit negative, right? So if you don't like quantum machine learning, you might like what I have to say, because it's a discussion around a barrier that comes up. And if you do like quantum machine learning, you might also like it because from a research point of view, this barrier is like a natural, you know, it presents like a sort of natural question of how do we overcome it to do quantum machine learning successfully. Okay, so before I explain the research question and, you know, hopefully something a little bit broader than that relates to you, I kind of just want to set the scene and provide some background and some motivation for the research question to just make sure we're all on the same page. So firstly, the types of models that we consider throughout this talk and throughout the study are basically these parameterized quantum circuits, right? So these are broadly, I think we can just think about them as you start with some initial state, you apply some parameterized operations to that state, and you're interested in measuring some observable, right? So I'll generally refer to this function as f of theta, and theta are these parameters in this circuit. And this model, this type of model, so here I'll speak a little bit like out of my depth of expertise, but like I think it comes up in lots of different areas, all I want to say, right? So not just machine learning, but like I think people care about these types of models, maybe in like simulating or like kind of moving from one initial state to some target state by parameterizing operations and then changing and tweaking them to get to some target state. I think these parameterized circuits also come up a lot in QAOA or optimization. In QAOA, maybe the output is not necessarily a expectation value, maybe it's like a bit stream or something like this, but I think there's still like this notion of parameterized operations in the circuit, right? So, and then of course, like the story today is more around this quantum machine learning kind of stuff. And people, I think, like try to motivate for these parameterized circuits as being more interesting in some way. Maybe they're more expressive, or maybe they are, I don't know, more interesting in some form. Like I'm in no way advocating that this is the case, but I think this is like the general belief in the quantum machine learning community is like, how do we use these models in an interesting way for machine learning? So in short, people care about these models, is all I'm trying to say, right? So if people care about them and they're widely used and they depend on parameters, we're gonna need to optimize them in good, clever ways. And classically, how do people typically optimize parameterized functions? Like what's the leading method? I'm actually asking. And I'll wait for a guess. Someone.
Gradient descent.
Yeah, there we go. Okay, good, very good. Exactly, like these gradient-based methods, right, are super popular, especially in classical machine learning. And so I just want to spend like a couple of seconds just giving a little bit of the background of the history here. And this is the only meme I'll put in the talk, I promise, and mostly because I'm a fan of the movie, Back to the Future. But really, like these gradient-based methods, and in particular for neural networks, this algorithm called backpropagation was something that came around that was super, super important, I think, for the rest of machine learning, that like the research that came afterwards. So I think backpropagation was originally actually discovered or invented in 1970, and then Jeff Hinton kind of like reintroduced it again in the 80s. And it was only up until like 2015 that like these deep learning models started to use backpropagation, because now we had like powerful computers to actually implement and train these models, right? Okay, so what is backpropagation? Broadly speaking, it's just a recipe to compute gradients, right? And we need gradients to be able to figure out how to update our parameters in our parameterized function. Okay, so I think that backpropagation was actually the first computationally efficient method for neural networks to figure out how to update gradients, which is quite cool. And one little throwaway comment I want to say is that it's a little bit more than just a chain rule. I think like a lot of people kind of who are familiar with these neural network functions kind of attribute the efficiency of computing gradients to the chain rule, because there's a lot of redundancy in the neural network function. And if you just naively write out the gradients, you'll see there's like a lot of repetition in things that come up in these computations. And so I think people make this statement that, you know, backpropagation is just a chain rule, but it's actually a little bit more nuanced than that. It sort of reuses intermediate information in the function to be able to store like stuff that's needed for computing gradients. So it's like also this on the fly storing and reusing of information that makes backpropagation so efficient. So this is like the nice thing about it. And then, yeah, I guess I wanted to put this timeline. This is my own depiction of this timeline to just illustrate that people knew about like perceptrons, neural networks for a while, and it really wasn't up until backpropagation that the success of these models that we have nowadays, like large language models, came around, because now we can optimize them. Okay, yes, also we need computers, large enough computers, but really backpropagation is like one of the key reasons we can scale models now up to like billions, if not trillions of parameters. Okay, good. All right, so what is this magic, magnificent scaling that I'm talking about that backpropagation achieves, right? Okay. So if you take anything away from what I say, it's this slide. So backpropagation scaling looks something like this, right? So it says like, okay, if you give me a parameterized function, maybe a neural network or something like this, and theta is, you can think of it as like an m-dimensional vector. So there are m parameters in your model, right? So m can be super large, billions, trillions. What backpropagation says is, okay, I want to compute the gradient, the full gradient, right? So this f dash of theta now is my full gradient vector. I want to estimate this gradient vector to within some precision. And what backpropagation scaling says is that the time that it will take me to compute this full gradient vector, which remember can be very, very large, is less than or equal to the time it takes to compute the function times some small constant here. So C1 and C2 are just constants. So if you think about what that says, that's quite amazing, right? Because naively you would think like you'd need, I don't know, maybe 2 function calls for each gradient component. There are like m of them. But what this is saying is that like to compute this super large, you know, potentially exponentially large vector of all the gradient components, it takes me the same amount of resources than it would take me to just run the function once. So that's like really nice. And the same is true for memory, right? And now I haven't said, okay, what time and memory means. And I think it like depends on the system you assume that you have access to. And I don't know, it can very quickly connect to deep things in automatic differentiation theory. So I put a reference there, and I don't know anything more about this. And for what I want to say, we can kind of abstract this away anyway, right? All I want to show you is that backpropagation, in terms of resources, has this really nice relative scaling, right? Where it's like the time to compute the gradient roughly scales proportionally to the time it just takes to run the function. And for neural networks in particular, which people love in machine learning, and it's the thing that we have to compete with on quantum machine learning side, these constants are quite small. It's like a factor of 2 or 3, right? So this is really quite amazing. Okay, so now obviously the research question comes in, is can we achieve this relative scaling resources for these parameterized quantum circuits that we saw in the beginning. And in particular, maybe even if we relax this constraint that C1 and C2 have to be small constants, maybe we can allow them to have some vague dependence on the number of parameters, maybe like some polylogarithmic dependence on M. Can we get close? And I should also just point out immediately that no gradient method at the moment in literature, as far as I'm aware, achieves this scaling, right? So this is an important question. Yeah, and does this make sense? Okay, and I'll explain the cost model and stuff like this just now.
Wait, can you say it again? So what's the, you're saying, so what's the statement?
So you mean, what's this last statement here?
No, so you state C1 and C2 are big O of polylog M.
Yeah, so maybe they're like, instead of constants, maybe they can have some dependence on M. Maybe they're...
Didn't make a claim whether it's possible or no yet, right?
Not yet, no.
So that's the question.
Yes.
So what do you assume about the function, basically? When does this hold?
Yeah, for backprop, I'm not sure what assumptions about the function are made, but this holds for neural networks, so that's yeah.
Maybe naive question, but why can't you do the classical computation on a quantum computer and then get?
Yeah, good question. You mean like just implement the function on a classical computer? That's true, you could do that, but the types of models that we're considering for the study are just these parameterized circuits in particular. So I want to get the scaling for those kinds of models. Yeah, okay. Yes.
Just naive question. I mean, like somehow the width of the network doesn't come in. I find it remarkable.
Yeah, no.
Is it true?
I think
because like I can imagine just doing like a bunch of independent functions and the gradient like will at least take me as much as like.
Yeah, that's a good question. And I think the width does come in somehow. And in fact, you can probably, I think you can actually even do better in some cases if you make some assumptions about your network than this like linear scaling that you have in the parameters. I think you can actually get better than that. And to be honest, I don't know. I don't know much about like the details of.
I mean, to sharpen like what I'm shocked by is that like you need to compute apparently m numbers, right?
Yeah.
And or at least you need, I don't know. So it's...
Well, yeah, I guess because there's two things at play, right? Like you have white box knowledge of the function, right? And there's like some repetition in the forward computation that's needed for gradients, right? So you can kind of store intermediate information and reuse it. So in some sense, you don't have to like repeat computation, if that makes sense.
No, but that's why I ask about the width, because there you sort of need to do something.
Yeah, I don't know. I can, yeah.
All right.
I'll read about it. I don't know too much, to be honest, about this.
Sorry, but I have a question. Like, shouldn't these constants be at least m because the gradient has m components?
Yes, that's what you would think naively, right? So indeed, like
how do you even output it if you can't choose? Like if the function outputs a real number, then.
Also, there is an m in here, right? There is an m in time and in memory for these things.
Okay.
Yeah. So
maybe I'm asking the classical propagation. So you are saying like we can estimate the gradient in time and the memory with infinity error. I mean L infinity error, right? So how about if we consider L2 error?
Yeah, you can do this too. I think then you would need like a higher precision or something like this. So I think as long as we just make this assumption that we have constant epsilon, and I don't think it changes. I don't think the story changes too much if you use L.
If it goes to the L2, then the precision scaled up to square root of b, right? So it's not
exactly. So to get back to constant error, you would need to have a higher, like high precision.
High precision.
I think so. Okay, cool. Yeah, so maybe just to come back to your point, Maris, like this is saying that like it's a constant times the time it takes to run your function, right? And that thing can have indeed like it definitely has a dependence on m. Okay, cool. All right, so yeah, so current methods for these parameterized circuits don't achieve the scaling, right? So this is something that's often ignored, I think, in most people's papers. And let's discuss like very briefly why this is not so straightforward to achieve. So the nuance of quantum gradients, I mean, I don't have to spend a lot of time here at this audience, but like, let's just go through like a elementary school grade 1 example, right? So let's imagine we've got one qubit and we just have one parameterized operation that we apply to this qubit. Okay, so we can draw the circuit even because it's so simple. And we can say, okay, we do some parameterized X rotation to this qubit, and it depends on parameter theta, and theta is a scalar here, right? So we can write the parameterized state explicitly, and we can also write its gradient out, right? So we can just drop this minus ix down. And then if we want to measure, let's say, like this Z operator, then we can write the whole function f of theta out for this simple one qubit example. And we can also write out the gradient. And hopefully, like, yeah, there's no mistakes here. But we can write out the gradient, and then we can simplify it, right? So we can say, okay, let's imagine that we just set all the parameters to 0, the theta to 0, and then we can see that this like estimating the gradient kind of reduces to estimating this expectation value here, right? We can kind of like ignore this imaginary part, doesn't really matter too much. For illustration, I just want to show you that, okay, we can kind of have this simplified setting where we set our parameters to 0, and then we want to estimate the gradient. And then when we have two parameters, like let's say now we do like an X, a parameterized X rotation and a parameterized Y rotation to our qubit. So now we want the gradient, and the gradient has two entries, right? And so all I want to say, again, simplifying the setting and setting the parameters to 0, is that each gradient component, estimating each gradient component, kind of corresponds to estimating an expectation value with respect to observables that don't necessarily commute, right? So if you have m parameters in your circuit, this is kind of a similar task to estimating m expectation values with respect to like operators that don't necessarily commute. So you can kind of get a sense of why this is not as straightforward as it is in classical with classical functions. Okay, so what is our cost model? In the study, we kind of make an assumption that, okay, we'll have m parameters, and they're these thetas that I mentioned, and each of these parameterized operations costs us 1, and its inverse as well, right? So if I apply like u theta, which is now a product of m parameterized operations, to some initial state, let's say the 0 state, and I create like my parameterized state like this, how much will this cost me in this cost model? So each parameterized operation costs me 1, and its inverse. And now I'm applying m of them to some initial state. So how much should this cost me? Somebody. I should have brought sweets, like Frank. Yeah? Yes, exactly. That's right. It wasn't a trick question. Indeed, it's m. Okay, and so then to like set up my function now, right, which is again just consists of m parameterized operations, this will also cost me m, right? And then typically to estimate this expectation value, we have like some sampling precision that we need to do, but this is not so important. Okay, so now for the gradient, we can write out the gradient of this function. This is the thing we want with respect to one component, theta k. And it kind of almost looks the same as the function, except there's like this, this partial derivative that comes in here. And so this will also cost me, to estimate this component, will also cost me m over some precision. But the catch, of course, is that this is just for a single component, right? A single component of the gradient. And now to do this for the full gradient, then naively, this is going to cost me m squared, right? So yeah.
Is it clear that if you can compute f with error epsilon, you can also compute f prime with error epsilon?
Is it clear?
You seem to be assuming that, but it's not obvious, because if you think about backprop, for instance, you're sort of tracing these things back through nonlinear functions. The initially error in the f value might sort of be blown up as you backprop back to the beginning of the circle. That's
true. Yeah. No, it's not. I don't think it's clear. I think if you make it a different, yeah.
Is it true?
No, I don't think so.
Okay.
I think the best you can do with epsilon is for the gradients, if you change a little bit the cost model, I think it's like square root of m times m, which is not necessarily the same as the forward, which is, I think you can get m, yeah. Okay. okay, so this is bad, right? Because this is giving us a quadratic scaling, and we want something like we don't want this. This is in our relative overhead kind of picture. This is saying the time to compute the gradient is equal to m times the time it takes to compute the function, right? And if you remember, we don't want this m here. We want something like polylogarithmic in m or something constant, right? And this is indeed what we get classically, like we get something roughly proportional, right? So this is this quadratic scaling in m, which corresponds to like m times the time it takes to compute the function. If we just look at what I showed you here, this is not very good. And as a computer scientist, you might be sitting there thinking, oh, well, you know, whatever, what does this difference does this make? I mean, it's quadratic to linear, who cares, right? It's all efficient. But in fact, you know, like hopefully this picture will convince you that it really does matter in practice. And in particular for like machine learning practitioners, it matters a lot. Like things that scale quadratically in the parameters, even though theoretically they have perhaps better properties to study them, people do not care, like they won't use them. They will just throw neural networks at it because they're just far more like amenable to optimization. So in this picture, the X crosses are the parameter shift rule, which is I think mostly how people compute gradients of these parameterized circuits these days. And this has this bad scaling, this quadratic scaling. And then the green crosses are hypothetical scaling we could achieve if we had some notion of quantum backpropagation. So you can see like already, if I had a day, which is, you know, quite a long time, I guess, to train a model, a quantum model, if I did not have backpropagation and I used parameter shift rule, I mean, I could only have a model with 9,000 parameters. I mean, there's just no way these kinds of models will then be able to compete with classical ones, right? So we really have to do much better than quadratic scaling. All right, so now let's, I guess, get into some of the results. And I think what we do is rather straightforward, right? It's actually just a collection of things that already exist and rephrasing them a little bit. So there's a couple of things that we can immediately say. So let's discuss the settings that we consider. So there are a couple of things, a couple of assumptions you can make about these parameterized circuits, right? So the first is that perhaps you assume that your input state is known. So you know how to construct it, or you know something about it. It's promised to be, I don't know, maybe something that comes out of a polynomial complexity circuit or something like this, right? So maybe you know entirely your input state, or you know something about it. And then of course, the more general thing is that like you don't know anything about your input state. You're just given input states and then you apply parameterized operations to it. And then the other kinds of assumptions you can make is that you have only the ability to measure single copies at a time. And then more generally, perhaps you can measure like multiple copies, right? So these are the kind of 4 settings that one can have in this picture. Okay, and then within these settings, there's already some stuff that we can say immediately. So for example, if we assume probably the most useful setting, I would say, is this one where you don't want to make any assumptions about the input state given to you. And you still want to be able to like achieve backpropagation by just measuring single copies, because I think in the lab, this is like much easier than doing measurements over multiple copies, right? So this is probably the most useful setting right now. But unfortunately, in this general case, we can show that backpropagation scaling is not possible. So this like relative overhead that I showed you is not achievable. And the way to see this is through a lower bound that comes from this paper over here. And what you can do is you can kind of take the simplified setting where, you know, like you have parameterized Pauli operations in your circuit, and you want to calculate the gradient with respect to every parameter. You set those parameters to 0, and you take every possible Pauli you can have, right? Every possible Pauli operation you can have. Then you can kind of use this lower bound to translate it back into our cost model, and we get this like quadratic scaling again. So we get this like bad scaling that we don't want. And so this in general is not possible in this scenario, unfortunately. I mean, of course, if you take some specific examples, and I don't know, you can make this work, but in general, this is not possible. Okay, so then I guess the next question is like, well, okay, what if I know some stuff about my state, right? So what if, for example, why did I put these references? Ah, yes, okay, that's fine, we'll come back to that. So let's say, for example, you can say that your state is given to you from a circuit of polynomial complexity, and I'll explain what that means now. So this is a bit of a weird result, and in the next couple of slides, if this doesn't make sense, it doesn't matter, right? It's just I put it in here because I thought this was interesting to say, and I thought this crowd might find it interesting. And it's a pity Jonas is not here, right? Okay. Okay, so if I make an assumption that my state comes from some circuit that consists of like polynomially many operations from some fixed state set, right? So it's like yeah, call it a state from polycomplexity circuit. So now yeah, psi has this property. So what you can see is that you can actually efficiently, like from an information theory perspective, determine the circuit that psi comes from using classical shadows, which is cool, right? But unfortunately, you can't like identify the state efficiently computationally. So there's still like a computational inefficiency in being able to learn psi in general. So let's pause there and like let's digest this a little bit, right? So what am I saying? So I'm saying that psi comes from this circuit of polynomial complexity. So how many circuits could there be, right? If we're assuming that psi comes from a polynomial complexity circuit. Well, I'm saying that there can be k of them, and k is like roughly n to the p of n, where p of n is some polynomial in n, right? So there's still exponentially many of these circuits, exponential in n. So there's a lot of them, right? And let's label every possible circuit that can come from these polynomial complexity circuits. Let's label them all as phi1 up to phi k. Okay, so there's exponentially many of them. Now with classical shadows, I can actually estimate the fidelity with respect to my target state and all of these exponentially many circuits, phi, using this shadow of my state, which we don't have to go into the details of. But interestingly, you can do this. You can estimate the fidelity with respect to exponentially many states with just a logarithmic number of copies, log in k, right? So this is polynomial in n. So this is efficient in terms of measurements, right? So we can make polynomially many measurements and kind of obtain all of these fidelities with respect to every possible state that we generate from a circuit of polynomial complexity. Okay, so measurement-wise, we can like get enough information, but of course, then we have to find the maximum fidelity, right? We still have to find it. And naively searching over exponentially many values is not, it's not going to be efficient. And then you might think, okay, well, maybe there's like a more efficient classical offline scheme we can come up with to find the maximum fidelity. But in general, this cannot be possible. And an easy way to see this is because these pseudo-random quantum states are states of polynomial complexity. So I don't know a lot about these states, but all I know is that they're computationally hard to distinguish from random states, right? So in principle, we should not be able to like learn pseudo-random states in polynomial time. This is not known to be possible. So yeah, this is a little bit of a weird result. All I'm trying to tell you is that it seems really unlikely, even if we like assume that our state comes from a polynomial complexity circuit, that we'll be able to like achieve the scaling. And in fact, in the paper, we kind of iterate through all known gradient methods, even when you know your state entirely, to show why it kind of fails to achieve backpropagation scaling. So long story short, it seems unlikely that we will achieve this nice backpropagation scaling with single copies, right? Okay, good. And now this is the last thing I will tell you. And the most obvious then next question is what happens when we introduce the ability to have multiple copies, right? This is surely more powerful, and maybe we can get some nice efficiencies there. And just a quick reminder again, like why it's not so straightforward, right? Especially if we look at the function and we look at the gradients, there's so much overlap in the computations that we like do in each of these functions, right? Or estimating the gradient and the function itself. Those U's, are largely very much the same. So why is it so, difficult for us to estimate or get better efficiency? And the answer, I guess, is just because quantum information is so delicate that as soon as we try to, peek into our circuit or measure anything, we destroy our information. So the intuition of now having multiple copies is quite beautiful, right? Why this would be useful is because perhaps by having more copies in memory, we can design better measurements such that we don't disturb our states so much so that we can reuse them again and compute gradients in a more efficient fashion like this. So this is like the intuition. Yeah? Okay, and this, kind of comes from a lot of papers. This is just one of them where they like have these spell measurements, so they measure like across 2 copies, and they already show some interesting things that can be done. And we basically port their protocols or their methods to show that indeed in the simplified setting that I spoke about earlier, where you assume like all possible Pauli operations as your parameterized operations and you set your parameters to 0, we can actually achieve backpropagation scaling, right? But this is a very simplified setting. We're setting our parameters to 0, and as soon as we like move a little bit away from this restricted case, things fall apart again. That scheme no longer works. And so you have to like start then questioning like, how hard is this gradient problem, right? I mean, why is it so difficult to get this scaling that we want? Is it impossible? So yeah.
What is the restricted setting?
Yeah, sure. So the restricted setting is just, imagine now in your circuit, all the parameterized operations are Pauli operations, and we take like every possible Pauli operation you can have. I think there's like roughly 4 to the n of them. And then you want to compute gradients with respect to the circuit. And then you set the parameters to 0 to just simplify the estimating the expectation values. So ultimately, it just reduces to like estimating trace of like your state with respect to every possible Pauli operation. And this can be, nicely done. Okay, so
why do you need this exponential? Like I thought if you have a fixed circuit, then right, you only need polynomial. You only need to compute polynomial number of expectations. But this is 4 to the.
Oh, sorry. I was just saying how many possible Pauli operations there are.
Yeah, but you consider yes, but you consider fixed circuit, right? You have a fixed. So okay, I don't understand where this comes in. This is number of possible Pauli.
We apply parameterized operations in the circuit, yeah, and then there are 4 to the n of them, is what I'm saying. Yeah. No.
So then possibility.
Oh no, actual parameters. We have all of them in.
Oh, you have like a full circuit of all possible, basically a mega circuit of all possible. Okay. Oh, why? Okay, fine. Okay.
No, I don't know. Like I don't know if this will be useful.
Okay, cool.
Okay, cool. So yeah, the last thing is this connection that we make to kind of illustrate the hardness of the gradient scaling that we want to this problem of shadow tomography. So just a show of hands, how many people are familiar with this shadow tomography problem? Okay, cool. Quite a few of you. Okay, good. All right, I think it's like really intuitive and beautiful and nice to understand. Hopefully I can convey it. Okay, so we're dealing with 2 outcome measurements, right? And you are given a number of copies of your state. And you know the measurements you want to make with respect to your state, right? So I call these like E1 to EM, capital M. And this capital M can be very, very large, right? So we want to do a ton of measurements with respect to our state. The shadow tomography task or problem is basically to output some estimates such that they are close to these expectation values we want to estimate. And in particular, using as few copies of your state as possible, right? This is the goal, like to output these estimates and not use that many copies, okay? So this is a well-studied, I think, problem now in quantum information theory. And yeah, I think it was like created by Scott, but yeah, I think this is not so easy. There's like, there's a lot of proposals that show that, and we'll talk a little bit about the best kind of little m you can get here. But what I want to show you is that actually, we say that, or we find that if indeed you can have an algorithm that solves this gradient problem with runtime t, then this will also give rise to an algorithm for shadow tomography with respect to a certain class of observables. We call them polytime observables, but this is not so important. With respect to these observables and also the same runtime t, right? So what is this saying? This is essentially saying that the gradient problem is as hard as this shadow tomography problem with respect to the certain class of observables. And if you're interested in these polytime observables, you can think of it as just like some Pauli sandwiched by two, like by U dagger, and U is just like some fixed polynomial circuit. And there is no known computationally efficient scheme for solving shadow tomography with respect to these polytime observables. Yes, Ron?
The gradient of what function F are you talking about?
Gradient components, yeah, with respect to like this parameterized, with these parameterized circuits that I mentioned earlier.
There was some observable value of psi theta.
Yeah, yeah. Should I write that explicitly? Maybe. Yep. Actually, here is the model. Does this help? Okay. And it looks very similar to everything I've showed you already, except we attach an Manzilla qubit to just like make things explicit. And yeah, anyway, it's not so important. But I think the main takeaway is that, so this shadow tomography instance with these polytime observables is not known to have a computationally efficient scheme. So this is a bit sad. But on the flip side, because there is this connection with shadow tomography and this idea of computing gradients, we can also port some known results and some known shadow tomography protocols to do backpropagation or to get scaling that's better for gradients, right? So the last thing we show is that we can actually come up with an explicit algorithm that gives us estimates close to the gradients. And I'm using a little bit of different notation here, sorry, but these are just the gradient components we want with respect to our model. And we can get all of these gradient components using a number of copies that gives us finally this like polylog scaling in M, and is roughly in line with our backpropagation scaling goal, right? So this was cool that we, I think, came up with this this efficient, like, whatever efficient means, backpropagation proposal. And I'll show you in a nutshell, in a picture, what it looks like. But there's a huge catch. The protocol, the shadow tomography protocol that we use here requires exponential memory. So there's still, even though we get like time down to something close to linear, we fail the memory requirement because the protocol requires storage of an explicit hypothesis state, which is like a density matrix classically, right? So this will scale exponentially in the system size. So this is a bit of a weird story because I'm like kind of telling you something positive and negative. So yeah, so in a nutshell, this is my last slide. This is the protocol that we propose. It basically makes use of two things: online learning and something called a quantum threshold check, which comes from this paper of Ryan and Costin at the bottom here. And basically, we use their results to kind of show that with a polylogarithmic amount of copies, we can kind of get enough information out to compute gradients. So how it works is we need, unfortunately, this sigma here. So sigma is like, you can think of it as a guess for your actual state rho, right? So rho is our state that we're interested in. Sigma is like a guess that we store in classical memory. It's a hypothesis state. And now we use some copies, we apply our parameterized operation to those copies, and we use sigma to compute an estimate for an expectation value that we're interested in. And then we can use this threshold check, which checks in a very gentle manner whether our estimate, our classical estimate, and our true estimate are close together. And if they are close together, we proceed using the classical estimate, and we like kind of go forward with the algorithm and do this again for the next gradient component. So you can kind of like bound how many mistakes you will make and how many copies you will need, and then kind of show with high probability you can get the information out that you want for these gradients. So yeah, so like that's in a nutshell how it works. And the details of like the quantum thresholds check and the online learning stuff, I don't know a lot about. I mean, they come from these papers. We really just take their theorems and repackage them. And the only difference is that we have these like rotations that happen after every threshold check, because you can kind of think of this as like applying like these update layers into your parameterized circuit somehow. It's like a little bit similar to like layers in a neural network, I like to think of it. Okay, good. So there are a ton of open questions, obviously, right? The first one, the most obvious one is like, well, is there an efficient computational scheme, I should say, for computing gradients of these parameterized circuits? Finding that out or answering that positively will probably necessitate like a breakthrough in shadow tomography. So perhaps more realistically, it's better to kind of think maybe there are special cases of parameterized circuits that train, better and scale better and perhaps are still expressive or interesting enough to do, like, I don't know, quantum machine learning. Or maybe it's time to consider other models, right? Maybe there's these variational circuits are maybe just like dead for quantum machine learning. Maybe there's no way they compete with neural networks. And perhaps maybe, like, you know, different methods for optimization would be useful. So we kind of talk a little bit about some gradient-free optimization techniques in the paper, and also show that indirectly they kind of fail at achieving this nice backpropagation scaling too. But maybe there are other more sophisticated methods that one can consider when it comes to optimizing these circuits. Yeah, and I think that's all I wanted to tell you about. So thanks for coming.